Hi everyone, this is Rick Morgan, your friendly comic book scientist. So in this YouTube video, I will go over in detail some more sciencey type stuff that people wanted to learn about. They want to know why does paper age? How does it get old? What does it mean? How can we stop it? So I review a paper I talk a little bit about why paper gets old, and then a paper that measures the aging process. In the future, I'm going to do more of these if people like them. If you do, let me know. I'll do more. This is an old Batman comic book, and this one has some aging in it. So you can see over here, it's coverless, but this paper is yellowing. It's brittle, well, slightly brittle, and it's from 1953. It is Batman number 192, and some of the pages on the inside don't look too bad. They're a little bit whiter looking, and we all like white to off-white pages, right? We don't like the yellow pages. We know what that means, and I'm going to talk a little bit about what's going on with this. Like, why does this happen at all, and is there anything we can do to stop it, and why do some books look worse than others? So that's today's video, and I hope you enjoy it. Let me know if you want to see more things like this or what interests you, and we'll talk about it. Okay, take care. Bye-bye. Hey everyone, I'm Rick. I'm your friendly comic book scientist, and I want to talk a little bit about this paper, which describes some ways to measure how fast paper is degrading. And of course, we're going to frame this around comic book paper, but I want to talk a little bit about what paper is and how it degrades, and hopefully we can learn a little something today. So paper is the primary component of paper these days is cellulose, which is effectively a polymer of something we call beta-D glucose. And that looks like this. These are chains, these are polymeric chains of what look like sugars, and they have these oxygens in between them, and it's this big network. And this network is what gives them their strength, and they can be kind of flat, and they form these things called fibrils or fibrils. And the fibrils make longer things that we call fibers, and these are what the paper pulp is. But anybody who's ever made this as part of an experiment in their class or used regular in a laboratory, like the filter paper, is literally just cellulose and nothing else. And anybody who's tried to write on that stuff can tell you that it's very difficult to write on. The ink doesn't spread. It can be torn very easily. It's weak when it gets wet. It sort of sticks together and rips. Anybody who's ever taken a piece of paper, just take a regular piece of paper like this, and you kind of fold it. And this has been sized, but and you just kind of like, oh, it's very strong. But if you get it wet here, just for a second, you'll see that it becomes very easy to break when it's wet. So that's one thing you have to watch out for, and that's even more so with regular cellulose. So it's just not really great. So we add these things called sizing agents. Now, sizing agents are, here I put some notes here that say that they are, and I will show you on my iPad. So sizing agents can be wet or dry, and they are things which you can add which help the ink stay on the paper. And they also give it strength, and they reduce dusting, they make it smoother, they make it lay flatter. They say that decreasing porosity and improving paper runnability, which is how it can be run into a sheet, or what they call calendaring. Now, in the old days, meaning from 1850s to the end of the 20th century, they used primarily alum, which is, well, let me go back and talk a little bit more about paper first. So the additives they use to strengthen the interaction between these fibers. The fibers are kind of sticking together. They want them to stay rigid and to be waterproof, and they want the dye to lose its polar end once it's sitting on the paper, so that it doesn't run, so it doesn't come back off in water, which is one of the reasons with my cleaning solution I've designed it so that it doesn't pull the ink back off, because we want to maintain the sort of hydrophobicity of the dyes, so they don't dissolve off the paper, which they could if it's aged or it gets too old or attacked. Now, paper in Europe, many hundreds or even thousands of years ago, was sourced from linen and cotton. That's what the two main things they made paper. They made a really strong paper, and they also used, of course, they used vellum, which was the sheepskin. They made strong structures because they were long and they were fibrous, and they found other ways of sizing them. We're not sure exactly what entirely, but all of them. But there were different sizing agents from town to town, and they made these long chains. They had about 3,500 or 4,000 different atoms per unit, And they have this hydrogen bonding. And you see these red, if you look in this graph here, you'll see these red parts are hydrogen bonding right here. So I'll show you some hydrogen. That's a hydrogen bond right there. That's a hydrogen bond right here. This is a hydrogen. You have lots of those. It adds to the strength while allowing it to still be flexible. And that's the secret of why these polymers of paper are so strong. Now, we don't usually use cotton and paper for writing on paper today. We usually use the cellulose. We use wood pulp. Now I have cotton paper. I'll show you a piece of it actually here. We use it for bank currencies and some other stuff too. But I can find a sheet of it. So this is microchamber interleaving paper, and this is made from cotton. This is cotton paper. It feels very different. It's stronger certainly and more absorbent, but much more expensive than regular paper. So wood is a much more readily available source, and we make paper, we print from it. Wood also contains other types of carbohydrates and something called lignin. Lignin is not a flat molecule. It's a three-dimensional polymeric material. I don't have a drawing of it here, but it gives woody plants their physical strength, like think of a tree, for example. So the wood pulps are normally purified to remove lignin so that they can lay flatter, it can last longer, it can be stronger. But newspapers and cheap books, and think comic books, they don't really remove much of the lignin. The lignin is just, they leave it because these weren't meant to be stored for 100 years. So the lignin is still here, and it's most present in very rapidly deteriorating materials. Why? Well, it gives places for other stuff to hide, impurities and things like these little pores that were in weak spots and cracks and crevices that are supplied by the presence of lignin. Now, why does paper go bad? So paper goes bad because, see, aluminum sulfate there's acid attack. Acid is the one attack. We say, oh, acid-free paper, acid-free this, acid-free. You don't really need to say acid-free paper anymore in the 21st century, but there are two principal methods for degradation of paper. The first one is acid-catalyzed hydrolysis, and that's what this is here. So you see, in this case, the cellulose here, this is cellulose, is hydrolyzed, meaning the presence of water, this glucose, this little sugar molecule, breaks off, and the paper will come apart and will also lose some of its hydrogen bond. So this is like the actual physical deterioration of the paper. It can also cause oxidation, which is the forming of two things. We have this carbonyl group and we have an aldehyde group, which can form in the middle where we used to have a hydrogen bond, and it will make the paper rigid, a place where it can break. Where there was a hydrogen bond, there's now another type of a less flexible bond, and the paper can become brittle in those areas. And that's one thing that happens: oxidation, and there's this acid catalyzed hydrolysis. So now it becomes acidic either by absorbing pollutants such as sulfur dioxide and nitrogen oxides from the atmosphere during manufacture, or more likely for the older books, for those of us who know the difference and can see this stuff, we have presence of aluminum sulfate. Now aluminum sulfate is called alum, and I put the early 19th century, should be 1950s, it should be. Sorry, this should just read the 19th century, so the 1850s into the 20th century, we would make alum. We get it from bauxite, which is it's kind of the reverse of this reaction that we're going to see later on. We take that with sulfuric acid and water, and we would make this material here, which is a sizing agent. That plus gelatin were the two main things they put on paper. So the sizing agent would, the aluminum sulfate hits water, and it globs up and becomes kind of gooey and gives paper strength. They found out just empirically it does this, and it sits on the water-soluble, the anionic ends of the dyes, and keeps them from dissolving off the paper again, and sort of protects it over time. But one thing that happens is, right here, water, alum, which is this stuff, plus water produces this stuff on the surface of the books, plus sulfuric acid. And sulfuric acid is what catalyzes this reaction here that helps cause degradation of paper. And that's only one of the things that happens, really. But Another one is that a second thing is, why does the paper turn yellow then, right? What's going on with that stuff? So the hydroxyl groups can be oxidized. Hydroxyl groups are the OHs in the paper. So anything that ends in an oxygen and a hydrogen is a hydroxyl group. So they get oxidized to aldehydes and to ketones and carboxylic acids. We'll see that in the paper here in a minute. And these lead to discoloration because these are called chromophores. A chromophore, anything with a double bond is chromophoric. And what those things are is this is like a ketone. This is a carbonyl group, and this is an aldehyde here, and these are all conjugated groups. These are all higher oxidation states of, you start with just regular, start with regular CO, and you oxidize it a couple different ways, and you get these different groups here. Now, these are called chromophores because they absorb light and they look kind of yellow to our eyes. And especially if they're on these sort of conjugated, what we call a conjugated aromatic ring, which is those things that you saw here, right? And conjugated means that there's double bonds that are one step over from one another. So they'll pick up light in the 300 to 400 nanometer range, which is absorbs sort of the low end in the UV, and so we'll end up seeing more of the reds and yellows because the blues are being absorbed, and they can decompose into these ketones. These ketones. They themselves absorb visible light, and since they do absorb light, that actually increases their susceptibility to these compounds anyway. What causes it? What kind of things? What are the sources of it? So the alum was for a long time a source of this dilute sulfuric acid, which would help to oxidize it, and then the oxidized components would leave these little broken ends. Hydrolyze it, and then the hydrolyzed ends would oxidize. Then there's nitrogen dioxide, which is just an atmospheric pollutant. If you live in a place with lots of NO2, that would cause it. So if sulfur dioxide is present in your area, that would cause it. Also, lactic acid and oils from your hands can cause it. They can be acidic just from regular handling. And to preserve paper, we want to deacidify it. And we can talk about that in a future paper or a future talk. But one of the things we do is we put a gas. We would use this diethyl zinc to permeate the pages, and we would neutralize any sort of, I can make a chamber doing that, I can show you guys, but we can neutralize any acids that are forming in our book, and that would stop it. That's one thing we can do. But that's not the purpose of this paper. So the purpose of this paper is to sort of see how we can monitor how fast things are degrading, and so let's check it out. All right, everyone, so I'm going to read you a little bit of this paper. That's the abstract, and what they do is, this is called cellulose oxidative and hydrolytic degradation in situ FTIR approach. So this was made in 2004, and it reads, this study concentrated on refining an in situ FTIR method to study accelerated aging of paper under controlled conditions. So I'll read the introduction, and then I'll talk about the experiment a little bit. It reads, it's hard to read because we're not seeing the whole page here. I'll shrink this up. There we go. It reads, millions of books worldwide are now menaced by paper disintegration through malignant and inevitably progressive degradation of cellulose chains due to acidic hydrolysis of glycosidic bonds. This problem is specific to paper produced over around 150 years between the mid-19th and the late 20th century, although the cellulose conformation of beta-D glycopyranose polymer is thermodynamically highly stable, meaning that basically they're saying that paper from the mid-1850s to the end of the 20th century has this problem. It degrades on its own. Paper itself, they say, is highly stable. It has appeared the addition of aluminum sulfate, alum, into the paper pulp acts as a catalyst of hydrolysis. Duh, we know that. Which en masse exerts detrimental effect to the cellulose durability. It means it gets old faster. Long-term consequences of the modification of the paper-making technology utilizing cheap ground wood raw material and sizing additives were not recognized and ignored for years, but it was not until the past 2 decades that the alkaline size paper technology replaced the acidic one and practically eliminating paper from the current archivistic use. So they're saying in the mid-80s they started to replace some of the paper with sort of advanced sizing agents, and they would didn't have this problem anymore, and it's almost non-existent today. So anybody says, oh, we have acid-free back and forth, dude, all bagging boards are acid-free now. Nobody has them anymore. So in order to solve the immediate problems associated with retrospective collections, mass book deacidification programs have been launched to protect those volumes which have not been completely damaged yet and to inhibit the cellulose degradation. At present, paper preservation tasks are being aided by the research on mechanisms of cellulose degradation, which is aimed at deepening our understanding of the degradation of phenomena and thus in return to blah, 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 they're making the paper better. Okay. Here, this is kind of an interesting one. This reads, according to the most recent findings, cellulose degradation should be regarded in terms of mixed oxidative and hydrolytic mechanisms, which they give some reference down here. And we already talked about oxidative and hydrolytic mechanisms a few minutes ago, where the two reactions are autocatalytically accelerated by active oxygen species. So we have to have air. If there's no air in it, it's not going to happen. And by protons, which is the presence of the sulfuric acid, in our case, from the alum mixing with water. Presently, paper degradation kinetics is based on formal rate laws, meaning that they just write down what they think they figure it ought to be. They need some not formal rate laws, but they want to do some empirical rate laws, get some mechanisms to see how fast this paper degradation goes, which, with better or worse results, are used to reproduce kinetic curves representing accelerated aging, blah, blah, blah. So what do? In this case, what they're doing is they take some paper and they put it in the oven in a vacuum and they dry it out. And so what they do is, I'll show you a graph. They measure and they try to see when is the paper gone. They measure at 100, 150 and 250 degrees Celsius. And they do it in dry air, humid air, and then they freeze out the water vapor. They have like what they call it LN2 or liquid nitrogen trap. They'll freeze out the water crystals under vacuum. And they replace them with deuterated water, which is DH2O. So here, they show you a graph of them drying out. They're just showing, because they're looking at a point right here where the water over time dries off the surface of the book. So they're showing, okay, we got all the water off of it. So we're going to put water back on and see where does that water go. Does it just sit there and still be water? Or does it actually end up in the fibers of the paper and become an oxidation product? So they're just telling you how they're setting it up. And this is an FTIR spectrum right here. So they're measuring, this is called wave numbers. And this, it goes from like 0 all the way like 3,000, but they're just showing this little spot right here. And then they say they tried different ways of measuring it. They tried measuring the hydroxyl bands. They don't show it, but they talk about it. And then the carbonyl region, which is this, they don't want that. That's the C double bond O. I'll show you. That's the thing I talked about down here. If I show you this graph, it's the C double bond O you see at the bottom there. That's it's growing. The presence of these things showing up means it's bad. We don't want to see those. And we're saying, oh, these things are taking up the water that was left behind. So how fast does this happen? So these guys are watching this, like you can see they're watching this over time. So they're watching this band right here grow. They don't really explicitly stop and say it, but they are. Do I have a way to draw on this thing? Sorry about that. My computer died for a second there. But what we're looking at is hydrolysis and oxidation. We're watching over time this peak grow. And that's them seeing this carbonyl peak growing and the whole thing aging. And this is what they're looking at. So another thing they want to do is to take the they're replacing some of the H2O. I'm just going to try to write this on the screen here with D2O. They took all the water out and they put some deuterated, meaning they use deuterium instead of hydrogen. It weighs twice as much, and they can detect that in the bonds later. So what they'll do is let the paper just sit, and then they'll come back and they'll measure it in a year, 5 years, 10 years, and see where that water, where that ends up. Where does it go? What does it look like? Get more specific information about the aging. And I haven't checked if they've got any updated papers yet. I will. I have a lot of papers to go through that I'll share with you guys in the future. And what they do is they look at these peaks and they monitor how they're growing, and they say, hey, this is what we're going to use. Oh, here's some of this oxidation mechanism here. Here, this little OH here, that's the hydroxyl group. These are the different ways that it can oxidize here, all these aldehydes and ketones and diethyl ethers and stuff like that, and how they're gonna look for it. So basically what they say is this is how we're going to monitor how paper ages. I'm that's the paper. You can read it if you want to. It's kind of fun. But largely, I just wanted to say, just to tell you that this paper exists, talk a little bit about the aging of paper. I've got a lot of papers I want to go over with you guys to tell you what's happening. But basically, how is this useful to us in comic book? Well, you know what happened and why. And if you want to clean a comic book, what kind of cleaner do you want to use? Do you want to use just water? Well, you can. It can actually, you can rinse some of the sulfuric acid away, honestly. Even if you just made it slightly basic, or you would. And so I make soaps and cleaners that are slightly caustic. They're just like 7.5 pH. They're very slightly, and they also are non-ionic, so they're less likely to take the ink off the pages. Now, normally these would be really crappy cleaners. You wouldn't want to use them to clean your house with because they don't clean a whole lot. They're extremely very gentle. They don't really do a whole lot, and you can't just sort of leave them in the book. You have to clean it once, and you take some water and you kind of absorb, because out comes the acid with it when you do that, and other impurities too. And it just helps the book last a little longer, and it kind of makes it look even too. Now, there are sizing agents in the book. Will they come off with some water? A little. They're not supposed to. Aluminum, the aluminum sulfate makes aluminum hydroxide, and that's global. It makes these globs, these gelatinous globs. They're not too soluble. It shouldn't come off too much. But the dirt and the oils and the things you touch should come off, and it should make at least the cover of the book, if that's all you're cleaning, last longer. Now, we can preserve the paper too, and I'll go over that and show you some examples of that in the future. But that's some science in a nutshell. Many people ask for more of it, so I hope that this helps. I hope it didn't bore you to death, and I hope you had some fun. Take care. Bye-bye.